tonight we're going to be talking about the equation of time. Some of you may not know what that means. It's not some kind of equation that will tell us how old the universe is or how old we're going to live. What it basically is, it's an equation, or it's like a graphical equation that tells us how early or late the sun gets to the middle of the day. I mean, normally you'd think that the sun would be the highest point in the sky, it's zenith on its arc across the sky when it's noon, but that's not always the case. Sometimes during the year the sun is getting there later, and sometimes it's getting there earlier. So that is what the equation of time is basically all about. And what we're going to do, and there's an example of Analemma. We'll be explaining that, how to get that Analemma and what it means. Underneath that Analemma, you'll see a very big sundial there. It's called the Large Sundial in Berkeley in Arizona. And I thought it was kind of a neat picture. That picture would have been taken in the morning when the sun is rising, but you have to take that picture many, many, many times throughout the year at the same time of day in the morning to get that kind of effect that we call the Analemma. Anyway, this is what we're going to talk about. We're going to talk, borrowing from Stephen Hawking here, about a brief history of time. I'm going to explain about how we used to measure time before we got mechanical clocks. Then we'll explain exactly what the equation of time is, and also what are the inputs that make up the equation of time. What are the things that influence that equation to cause the sun to be late or early, getting to its high point in the sky every day during the year. And then we'll talk a little bit about the Analemma, and if time permits, we'll have a look at some of the other planets in the solar system and see what they have to say about their Analemmas. Anyway, moving on, there's Tower Bridge in London, and there's got a beautiful sundial there right outside Tower Bridge. So just a little bit of history here. This equation of time, it's from the medieval Latin at Equator Ilium, and they're using the word equation in this sense to talk about reconciling a difference between things. And here we're talking about the difference between the real moon, according to your watch, and the sun noon, when the sun is at its highest point. And they're only the same a couple of times a year. So we're talking about that difference. You know, how early or late is the sun arriving at noon there. Now this difference, it's been known since antiquity, in BC times, mostly from the Chaldeans from Babylonia. And yet, this is the thing that really surprised me. Up until about the middle of the 1600s, the sundial was the official way of measuring time. Accurate mechanical clocks had not been invented before the mid-1600s. And that really surprised me, is that, okay, it's time to work, time to go home, it's all based on the sun. But that was their most reliable method of measuring the time, even though they knew it wasn't completely accurate. But that's what people used to do. And like I said, it was in 1656 that they managed to devise an accurate mechanical clock that would keep time. And it was after that time, they eventually solar time sort of became obsolete once people put their faith into mechanical clocks, and that became the new standard after that. But it came as a surprise to me to know that it was only just a few hundred years ago that happened. Anyway, I've already explained that. It's the difference between sun reaches daily zenith compared to the actual noon time. Okay, now, there's two factors that go into making that equation of time. Now, the Earth's orbit around the sun is very slightly elliptical. It is an exaggerated elliptical orbit here. And you don't have to be a rocket scientist to appreciate the fact that when the Earth gets to its closest point to the sun, known as the perihelion, that's when it's going its fastest. And when it's the aphelion, the farthest point, it's going its slowest, which means that the speed that the Earth is going around the sun is not constant. So if the sun is really whipping around near the perihelion right there, the Earth, after it goes around, it's got to turn, like every day normally, the Earth has to turn an extra about 4 minutes of turning before it's facing the sun again, because sidereal time based on stars is not quite the same as solar time based on the sun. And what we call the real time is what we call the mean solar time. What's the average length of the day in the year? You know, the year being about 365.24 days, I think. So that is going to make a difference to having the elliptical orbit. It's going to make a difference to when the sun is going to tell you it's noon and when it isn't. So that's one of the factors that affects the equation of time. Now the other one is not quite so intuitive, but it can be explained, but it's just doesn't jump out at you so obviously. Now that top diagram, this is showing the path of the sun. Starts off at equinox here, goes through the constellations, and it's north of the equatorial plane, which is why the sun is higher in the sky this summer. And then in the fall time, it goes down below that, and the sun is below the plane of the ecliptic there. So this is the path that the sun is taking across the sky during the year. Now, what makes this a little tricky is that let's say we're at the one of the high points or low points, here or here. All of the motion of the sun is going in an eastwards direction, so we'll go like this direction. But when you're actually coming down the graph here or going up here, as you're going down, you find that that motion is now going this way, which means it has an easterly component and a southerly component. Then when it comes down to the bottom part there, it's all easterly, and then here it becomes a combination of east and north before going easterly again. Which means that, if you remember vector analysis in high school there, if you've got something that's moving at a constant, let's say if the orbit of the Earth was perfectly circular around the sun, which means that the motion of the Earth along the the apparent motion of our sun along the path like that would be at a constant speed if the orbit was circular. So if we assume for now that the orbit is circular and the sun is moving at a constant speed along there, when it's at these points here and here, you've got an angle, which means that the sun is not just going east, it's also going in another direction as well. So the easterly component of its motion is not as great as what the easterly component would be here and here, which of course is 100% of the motion. So you look at that factors together, the sun is moving it's moving fast easterly here. Here it's not moving so fast. Here it's moving faster again, and here again it's not moving as fast. And that again will make a difference between when the sun reaches its local noon. Now if you combine that with the elliptical orbit, then you can see that we have two things influencing what is going to form the equation of time there. Now this is another graph that just shows it a little more clearly, and the reason I put that in as well is because this is showing you, here's the summer solstice, autumnal equinox, winter solstice, vernal equinox or spring equinox, and this one shows the constellations a little better as the sun takes its path across the sky like that throughout the year. So is everybody with me so far on that? Have I made this clear, the two factors that go into producing this equation of time? I hope it makes sense, because for the longest time I had a hard time trying to understand myself why the tilt of the axis will influence when the sun gets to local noon. But then when you start realizing, how it moves across the sky like this, you can see how the easterly component of the sun's motion is constantly changing. And that's what makes a difference, because we measure time from east to west across the sky. We're looking at local noon is when the sun is at its high point there. Okay, now I wish I could have split this into 4 sections to show you, but if I did, then I'd lose the motion of the sun. Now, if you look at the top left-hand one for now, the effect of the orbital eccentricity, because you've got one period, one near point and one far point, you've basically got one big sine wave, throughout the year when the sun is slow or when it's fast. Whereas the effect of the obliquity, or the effect of the tilt, because you saw that you know, the path across the sky, you've actually got like a double sine wave in the year there, eh? And if you combine these two together, you end up with this here, which is called the equation of time. Now it's interesting because when it's at a minimum here, like in here, this point, it's a 15-minute difference between when the sun and the gets to the local noon. But you can see in both cases you've got a minimum here, almost coinciding, so the two effects combine here. When you get to this point, you know, they're kind of interfering with each other, so you don't quite get the same maximum and minimum here. But then towards the end of the year, you get a maximum on both of them, so you get a big maximum up here towards the end of the year. So you get this two superimposed sine waves on each other, and they basically look like this. And what the time difference is showing you is, again, the apparent time by the sun versus the actual mean time, like the average daily time that we go by, according to our clocks. Now, if you can imagine that first picture we showed, where we showed a very basic sundial with a stick in the middle forming a shadow. Now, if, let's say you took a photograph of it, let's say you looked at that sundial every day at noon, every day, say. It doesn't have to be noon, but as long as it's the same time every day that you look at that. And let's say you made a little mark on the ground where the shadow of the pole, the end of the pole is, the tip of the pole makes it shadow, you know, and make a mark there. And then you do that all through the year. It's easy to understand why in summertime the sun is high, and wintertime it's low. So the greater the tilt, the longer the axis is going to be this way, so to speak. But you've got these differences this way as well, showing you how late or how early, you know, the differences between when the sun gets to local noon there. And this effect, like I said, you can get it from the sundial, you know, sort of mark a place in the ground all through the year to see where the end of that shadow of the stick is, or you can take a photograph of the sun at the same time every day in the sky, assuming there's no clouds at all, and then you can get to see how the sun moves, if you like, all throughout the year. And this is where this Analemma comes from, as it's called, this figure of 8. Okay, just want to sort of decomposing the equation a bit to show you that this shows you a little bit more obvious how it works. The dotted line here is the graph according to the elliptical orbit. Number 2 is a perfect sine wave here according to the obliquity or the tilt. And you can see now when you combine those two graphs, you can see why you get a fairly good maximum here. But here, they interfere with each other. You've got maximum and minimum up and down, so it's not very much of a minimum here. There, they're all together. And then here, they're sort of interfering as well, so you don't get much of a maximum here. But over this side, you get the dotted line and the dashed line, both sort of on the negative, so it amplifies the effect there. So this, I hope, sort of explains what goes into that equation. And again, there's what it looks like. And the way we would read this is that, let's say in the early part of the year, what you have to do is, because the sun in the winter, it's, you know, the closest point of the Earth to the sun is on January the 4th, which means that is where the sun or the Earth is actually moving fastest on its orbit, which means that the sun is going to get to local noon a little slow because the Earth's ahead of itself. So this is what you have to add to the sundial to get the real time. And as you see, it's almost 15 minutes off there, and that's quite considerable. Whereas down in the fall here, just before winter, you've got more than 15 minutes because you've got, you know, the combined effect of both the minimums of the sine waves really combining there in a positive sense, eh? So that is basically what the equation is all about. Now, it's usually presented in a form like this, so you can read it to see how much you have to adjust, you know, solar time to mean time, as we call it, or clock time. You know, and it's a neat little device, and sometimes it's tabulated as well. But I mean, it's much clearer if you can see what's going on here with the graph here. Now this is the Stargazer's Almanac. Like Sky and Telescope do this every December usually. And I know you can't see much from that picture, but if you look at this one here, you can see here they're actually showing, this is the equation of time that they're showing throughout the year here. And I know you can't read it, but I couldn't get a high definition image of this. But here it says sun slow, so it's slow getting to the real moon in the earlier part of the year. And if you look later in the year, there's the big negative there, and I know this is illegible, but that says sun fast at this point there. So the sun is actually ahead of local moon, you know, later in the year there. Okay, the Analemma. This is another picture showing you, you know, where the sun is. Like here it's going to be slow in the earlier part of the year. And then when it crosses another equinox, it's still slow. Because this is an accumulative effect day by day, so it builds up a bit, and then after here it starts coming down again. And then when we get over to May in the springtime, it's over here. And then you can see it makes this path across the sky. But in reality, that's an exaggerated shape. This is what the Analemma would look like if you actually took a picture of the sun, let's say once a week, or when it's not cloudy, you know, and try to remember to take the same time of day and the same angle with the camera. This is basically how the Analemma would look in reality. But this is exaggerated here just to show you what's going on a little better. Okay, here's another example of some analemmas. Now, that analemma would be in the early morning. As the sun rises, it's coming along the path like this. So, at different times of the year, you know, the sun would sort of appear like this, according to what time of year it was. At noon, it would look like that. And towards sunset, it would look like that. So, if you wanted a perfectly upright lemma, you'd have to sort of start taking your photographs at as close to local noon as you can every day. Okay, now here's an example of Analemma. The reason I did this is because you would think intuitively that on the shortest day, the shortest day, you would almost expect the sun to be rising at its latest time, and then on the longest day, you'd almost expect it to be the opposite to that. But as you can see at the solstice here is where the sun is. It's still about the horizon there. Whereas you have to wait till January 3rd before the latest sunrise happens. So it doesn't happen on the solstice, it happens you know, a couple of weeks later, because that is when the sun is at this point now. Whereas this point here would be the solstice. And then on this side of it here, you know, this would be 12 minutes before sunrise there. Whereas in the evening time, on the same day, the earliest sunset in the evening is not going to be on the solstice, but it's going to be on the 8th of December. That is when the sunset is going to be at its earliest. So your longest evening, if you like, is going to happen around about the 8th of December rather than the 21st. And by looking at the Analemma, where the sun moves all through the year, that fact becomes more obvious. But if you said to somebody, oh yeah, you know, the sun is not, doesn't set at its latest at the solstice in winter, you would think, well, that doesn't make sense. But if you look at it this way, it really does make sense, doesn't it? Okay, it looks like we have a few little bits of time here. Now, one of the things when I was preparing this talk, I was curious as to know what was happening with the other planets. I mean, every planet has a slightly different elliptical shape to its orbit, and they all have different tilts as well. And I was particularly interested in Uranus, because that's virtually tipped on the side, and I was kind of wondering what, if anything, the equation of time would look like there. But anyway, if we look at Mars, if we see that there's only one basic lobe instead of two, it means that the eccentricity is the predominant factor. Like, there's only one more planet more eccentric than Mars, and that's Pluto, if we're still calling it a planet. So Mars has got a fairly eccentric orbit, which is why once in a while, when the Earth is at its farthest from the Sun, and if Mars happens to be at its closest point, as a conjunction happens, Mars will appear at its biggest in the sky. So that's what Mars's Analemma basically looks like. Jupiter, again, slightly elliptical orbit, but there's no tilt to speak of. It's only about 3 degrees tilt of Jupiter. So that one is much more circular, whereas Mars, because it does have sort of a tilt to its orbit as well, but it's overwhelmed by that the eccentricity of the orbit is. So it's sort of the oval shape, but you can see towards the end of the oval, it's almost trying to cross over there, but doesn't quite do it, whereas Jupiter's much more sort of oval shape there, eh? Now Saturn, that has got ellipticity and good tilt, and as you can see, there's a little bit of a crossover there before it does its loop here, but not very much of one. So you can see how all these planets are different. Now Uranus, I think what they're trying to show there, with Uranus being on the side, they're trying to show how it would affect during the day, during the year, but it's a little bit difficult because once you're just a few degrees away from the equator, the equation of time is kind of meaningless because it's basically half a year of sunlight, half a year of darkness, so it doesn't really make a lot of sense with Uranus there. But I think what they're trying to indicate in that picture is that it sort of does go to the other, right across like that. Neptune has also got 2 lobes, and it's saying that what that would mean then, versus Mars, which has got a higher eccentricity, this would imply that the eccentricity is very, very low. It's almost a circular orbit, but the tilt by itself gives you that nice figure of 8 pattern. And if you look at our old friend Pluto, now Pluto's a bit of an oddball as well. It's sort of a double dwarf planet, if you like, circulating around the epicenter. And it's not tilted on its side. It's, oh boy, if you imagine if the direction of rotation of the planets, we consider it anti-clockwise looking down, Uranus is just beyond the 90-degree mark, but Pluto's down here somewhere. So it's kind of rotating the wrong way as well, but not sufficiently close to the equatorial thing that you can't make sense of the equation of time. So that gives us a nice kind of double lobe as well there, eh? Now here's some other pictures that show it a little more clearly. Like there's the Martian Analemma, and you can see the eccentricity there, 0.0934, and that's quite eccentric. Like Earth itself is just 0.167, I believe, and the tilt of Mars is even greater than the tilt of Earth by a degree or two, but still not, because the eccentricity is so big, the Analemma will not cross over, because eccentricity dominates it completely here. So looking at Jupiter, let's see. There again, it's got eccentricity 0.04 something, which again is more eccentric than Earth, but with the tilt of only 3 degrees, that's virtually negligible. So the one side wave is the one that dominates on that case. Now here's Saturn, and again it shows you, it's got a fair amount of eccentricity there, 0.05, it's quite a bit more than Earth. And it has a much greater tilt as well, nearly 27 degrees. So the tilt itself will give you the bipole here. You've got one lobe here, even though it's a small one, and a big lobe here. Whereas the eccentricity almost dominates it. Like if it was a little bit more eccentric than this, then this would look more like Mars, and you wouldn't get that crossover there. Now, the way this website describes Uranus, I really can't make any sense of this at all. It's almost like trying to say every day it looks different, and this is the path the sun would take. But you can see the tilt there, just greater than 90 degrees, which means that if you're looking down on Uranus from the top of the solar system, it's basically rotating the wrong way, but only just. And this has got a fair amount of eccentricity too, 0.04. And when you look at these comparisons, you can see just how circular the Earth's orbit is compared to these other guys here. Now, if we look at Neptune, look at the eccentricity, virtually nothing, 0.0086. So the big sine wave on the Neptune will be very, very minimal, and that's kind of indicated by the purple lines here. Whereas a tilt, quite a substantial 28 degrees, so you get a double lobe with that, but because the eccentricity is so small, the double lobe dominates, and they're almost equal. Now, but look at Pluto. Now, Pluto is a little different. It seems that the two sine waves for the tilt and the eccentricity are almost in phase together there. So the net result is, well, it's sort of, yeah, you kind of got, it is sort of a bi-wave as well. It's interesting that here's the eccentricity, here's the tilt, but they seem to sort of be more in phase together than Earth, because it all depends on what time of the year that you hit your closest point to the Sun. So none of these equations of times are really anything like Earth, but it's amazing that someone actually took the trouble to figure all this out. I was quite impressed, but I thought it would just give a little bit of variety, just to show you that you know, planets are different, definitely. And here's a more modern sundial, and again, the way they've got the this almost looks like the figure of 8 shape here. And I guess I'm not sure how the markings are, but it's quite obvious apparently when you read the time on this device here in front of the ray, it will actually, you can read off the exact time on that sundial. So that is a more modern sundial now that takes into account the equation of time. So basically, my goodness, I'm on time, and that's basically all I have. So I hope I've made it a little more comprehensible this time, but if there's anything I didn't explain properly or is not quite clear, please don't hesitate to ask, because I don't want people to go home confused. I want people to feel that they really understand a little bit more about the equation of time now. So any questions for anyone? Yes? No? Yes?
I'm just wondering if I can get one of those, but maybe a more modest one for my backyard.
It would be nice to have, wouldn't it?
Does anyone make those? Or is that just totally custom?
They're probably not cheap though, but
That'd be really
yeah,
cool.
it would be really something to have, actually.
There's a large one in Pinawa. Not like it's
Yeah, as Jerry was saying, there's one in Pinawa, right?
Yeah.
Yeah. So you can go borrow that one.
Bring a truck. Forks.
Yeah, well, that'd be a little hard to lift. Thanks, man.
Okay, good evening. There's quite a few of you for a snowy drive. Welcome everyone. This is the Winnipeg RASC November 2017 meeting. If you're not here for an astronomy club meeting, you're in the wrong spot, but I recommend sticking around anyway. We're fun and we legit have cookies. So tonight, I'll give you the rundown of what we're going to be doing. We just had the beginning session with Nick talking about starting time. We'll have what's up with Brian, who's here, and we will then do what's new with Ian. So I'm just going to run through some announcements, and then we'll get into the fun stuff. Calendars. Stan, are you here? No Stan. Okay. I would say talk to Stan. In lieu of Stan, just talk to me. I believe the calendars are in. I know that they were shipped out recently. I haven't talked to them recently, but yeah, they are going to be $12. So the Winnipeg site subsidizes some of the cost of these. So if you want to buy a calendar, I highly recommend it. There's a certain member in the group that actually is actually has his photo in for March. I won't say who it is, because that would just go straight to his head, but there is some Winnipeg representation in here. We are doing a photo exhibit at the Blankenstein Gallery. This is like the Berenstain Bears all over again. For people that get that reference. This is actually, so this is at the Millennium Library. We did this a couple of years back. And basically, if you have really pretty astrophotographs that you would like to show off to the world, talk to Ralph. Just get them printed off, and you can, and he'll work with you to get all the work done to get them put up. So that'll be happening in April. I don't know if Ralph has a deadline just yet, but I would highly suggest getting going on it and getting in touch with him when you have some stuff to submit. The Oakhammock Marsh Astronomy Night continues to happen every month. This month will be on Thursday, November 16th, from 7 to 10 p.m. If you show up to help out, particularly with a telescope, then they'll waive the entry fee of $10. Although $10 is not that much money for just to enjoy a night under the stars and some good presentations. I think the one that they're doing this month is actually going to be on astrophotography. So if you'd like to learn about that sort of stuff, I recommend going. Explore the Universe. So Explore the Universe is a program that the RASC has. You don't even have to be a member to participate in it. Basically, you get a list of objects, and you're asked to go and record your observations of these objects. And then if you record all the required objects, you submit that off to the RASC, and we will facilitate that for you. That's something that Dennis has been taking on, and you get a certificate back saying, "Great, you've done this." And what I love about these programs is that it's a really good way to give you some focus. You may have heard this before, but the universe is really, really big. And it can be hard to pick stuff. It can be hard to know what should I be looking at. And Explore the Universe is fantastic, especially for beginners, because it gives you a list of reasonable objects to go and try and hunt down. So I recommend checking that out. Now, the main reason why I'm including this sketch up here, it's a very nice sketch, is that the Explore the Universe program previously required that you actually sketch your stuff. You don't have to do that anymore. It's no longer a requirement. I would recommend sketching it. I would still highly recommend sketching it, even if you're terrible. I will never show my sketches to anyone else. Don't ever ask me to show them to you because they're embarrassing and terrible. But I like looking back at them because it gives me just an idea of like this is what I was looking at. This is what my eyeballs saw that night. It's not the most artistic, and some people are very good at it. I'm not, but I still recommend doing it. It's a really good way to record your observations. Yeah. So you might be asking yourself, Brendan, why are you showing me Living Magazine? So this is I'm just dragging out the eclipse stuff. I'm going to bleed that rock until it's dry. So I have a friend who is the editor-in-chief of this magazine in Dallas, Texas, that has a distribution of about like 750,000 or something like that, right? And he reached out to me and he said, "Hey, I heard that the one in 2024 is going to be coming right through Dallas, and I'd like some content, to be able to put in the magazine. Would you be willing to supply anything?" And I said, "Yeah, sure, why not? No big deal. Like, I'm so excited to talk about it, whatever." Right? So I reached out to the club, and a few people did actually contribute. And sent me their pictures and stuff, and I forwarded them off to him. And members of the Winnipeg RASC now have their material printed 750,000 times-ish in the city of Dallas, Texas. Life is interesting. What's funny is that, so I've got a copy of it down here, and there's actually, there's a digital link that I could send out as well. What's really funny about it, though, is that you'll notice that it's called Talk of the Town, right? North Texas experiences eclipse. Now, he's talking about the partial side of it. So I made sure to, like, work with him, make sure there's a faster straight and everything like that. He never actually explicitly says that we're from Winnipeg. So that is actually like the little quiet white lie that's happening as part of this article. We had some fun with it, but yeah. So we got the phone, some cool pictures. So these are the buddies that I traveled down there with, and we took some of these shots. This is from Bill Crosney, and this one was from Dennis Lyons. So that's one of Bill's as well. The diamond ring right there. So yeah. So I'm putting on my resume that I am now a published photographer. Okay, telescope loans. Stan's not around, but he's the guy who handles telescope loans. Basically, we have a suite of telescopes that you, if you are a member, you can take out for a month at a time, and there's no charge. That's about it. So, if Stan were here, he would have some knowledge about what the current status of it is. But usually, the telescopes are in fairly high demand. But if you get your name in, you can get on the list, and you'll be sure to get one at some point. Go on the observatory. Is Brian here? Okay, oh, Brian. Brian is the observatory director. We do have an observatory. It is just south of the city. This again is a member of PERC. You don't. By the way, in this report, you don't actually have to be a member to be in this room right now. That is a common misconception that I have that I've found with a lot of new people. So if you think you snuck in or something like that, not paying, you get it's totally cool that you're here. But the observatory itself is actually for members, and if you want to get access to it, you totally can. You just have to talk to Brian whenever he shows up. But if you want to, there's a contact form on the website, or you can just talk to me. That's cool too. So, Brian is, speaking of Dunley, Brian is planning the next Members Observing Night as just a Leonid meteor shower giving. So the Leonids are not a terribly spectacular meteor shower, but they're good and worth going out. And I'm pretty sure the moon is in a good. I think it's pretty close to the moon. So yeah. So he'll be doing that on Friday the 17th, which is a week from now. How did that happen? There. Time flies.
There he is.
Hey, look at that. Nice time. I was just talking about you. You're up. Listen, do you want to?
Yeah, please.
Okay. Ian, would you mind jumping in? Oh, I don't know. Okay. So yeah, so that's everything for announcements. Unless anybody else has anything else to bring up, I think I covered everything. I'm just gonna wave my hands.
Sunday morning, conjunction of Venus and Jupiter.
Monday morning.
I assume Brian will talk about that, but
Okay.
yeah. But if he doesn't, we will.
I don't know if he's going to come tonight.
Yeah. We'll scold him if he doesn't bring that up. But yeah, there's a conjunction Sunday morning. It'll look good. So. Monday. Sorry. I'm on holidays. I don't remember what day of the week it is. Very good.
Yeah.
Working on a master.
Buy a PC.
Okay, so now we've dealt with the PC to Mac conversion. Ian has sacrificed his whatever on the altar of, he's cleansed the,
No blood involved.
yeah,
No blood involved.
metaphorical. Anyway, so Ian will be giving us a rundown of what's been happening in the science of astronomy.
So everyone can hear me fine? Good. Okay, what's new? I'm perfectly lazy this time around. One item. One item. Okay, and that's because, you know, if you look back at this event a few years down the road, you realize perhaps just how significant it is. So we have finally detected gravitational waves from a binary neutron star system. Okay, and so this is the title of the paper that came out middle of the last month. The actual observation was just before the eclipse. I know what I was doing, and apparently some of the people who are involved in some of this work were also preparing for the eclipse, and this was just sort of happening around about that time. You will notice that there's only one author. Not quite true. There's about 700 authors and any number of affiliations. All right? So, what was the event? This little line across here. Actually, what it is you're having to look at frequency and time. And so what we have is a sweep from about 35 hertz all the way up to around about 250 or so. And a very, very strong signal. And what was really interesting about this is that there was a gamma ray burst detection around about the same time. All right? So that immediately put people on high alert. Okay, they said, oh, this can't be just a coincidence. So the other detectors are checked, and by the time everybody gets together, lots of text messages float around saying you need to be ready to make some observations. 5 hours later, observations from Mercury and also from the Fermi satellite that was responsible for the X-ray burst detection. Okay, and that they have things localized in the sky reasonably well. What does reasonably well mean? 28 square degrees. All right, but it turns out, you know, that this is actually much more doable than you might think, especially when you've got lots of people sort of involved. So these are the actual events, and it turns out that the Virgo one, you were able to infer what part of the sky it should be in. Okay, because as you can see, there's not much of anything going on there in that particular detector. Okay. So, but anyways, they managed to give the observatories a location on the sky in which to look. Okay. And alerted everybody. Who's everybody? Well, they're scattered all over the world. Something about 70 observatories or something sort of involved in this particular search. And lo and behold, somebody took a photograph. Okay, so we have an image of it. And what is really important with these kinds of events, of course, is that they don't last very long. So you get people to sort of jump on it. You've got 70 observatories on the go, getting data. You see 4 days later that you've got quite a difference in the activity. So, what actually happened? Here's an animation of 2 neutron stars. Basically, this is an in-spiral event, so what they're doing is they're moving faster and faster. They come in and they actually merge. Okay. And so that's the prediction, okay, and the observations bear it out. Now that's got to be really cool. Really cool. Okay. So what you saw there was sort of visible animation. And here we have one, probably I have to hit that again. Okay, so now you're looking at basically a simulation of the gravitational waves. So what you see is increasing frequency, increasing amplitude. All right, and this is the signal basically that we're going to detect. You can see the sweep through the frequencies in time, an increase in amplitude of the signal. And this thing will settle down after a while, so there's be a little bit of rimming, a little bit after, and a dampening of the signal. And you finish off with a more massive neutron star spinning more rapidly than you sort of started. So, the beautiful thing about all of this is that you've got so many observations you can actually pin down what happened, right? And you have lots of good data to play with, and you get to find out which theories you can throw out in a hurry. You're able to determine the masses actually fairly precisely as these things go. You can start off with basically a couple of models where you've got things which have lower spin pairs or higher spin pairs, but you actually do have constraints that are quite tight. And this really contributes significantly, if you like, to our understanding of the dynamics of mergers. Right? So this is one of the things that comes out of this almost immediately. The cool thing about this too is I can get a distance measurement out of this. Okay, where I don't know how far away did this happen, and there's some other things which are important, basically, to the people who are actually involved in sort of the lead and maintenance of these things. So what's really all the fuss about? Well, this is the second multi-messenger observation that we've ever had. Does anybody know what the first one was? Wow. Supernova 1987A, okay, when there's a neutrino event, okay, with it. And of course, we associated with that event. And of course, this is, if you like, a prelude of things to come. What this observation allows us to do, of course, is it tests some of our theories of gravity. Uses a whole raft of theories that we can actually now toss out. And you might think, oh, that's too bad. But no, that's a good thing. Okay, I'd like to know which way you're headed. It's nice to be able to sort of narrow down your focus. The speed of gravity. Has anybody heard of the speed of gravity before? Well, it turns out, I told you that you've got a gamma ray burst very fast, or a transient gamma ray event that occurred 1.7 seconds after the fact, after the coalescence. because we've actually managed to make that identification with the object, you know, that they're both missing sparks. There's an independent determination for the Hubble constants that doesn't rely on the distance ladder. As you probably know, distance ladder is built up with successive little observations. You start off with basically triangulations to nearby star systems. You use any means you possibly can to get a little further out and get that distance determined well. And you just keep sort of popping out all the time. And this is independent of it and gives you a reasonable value for it. So there's an upper limit of like 82 or lower limit of 60. You get something about the geometry of the gamma ray burst event. And one thing that we have always suspected when you've got the binary neutron star merger is you'll end up with short gamma ray bursts. So like a lot of things which have been puzzling in the past have become a little more clear. And so you can see now maybe why I spent as much time as I did on this just sort of one point.
Any questions on that?
I have a question.
Sure.
So after the collision and the merger of those two things, is there an effect so that it looks like in the universe you've dropped a pebble in a clear lake and you get rings of signal coming out after the event?
It's actually during the period of coalescence. It turns out that there's another paper that was published very soon after looking for just those kinds of things. Okay. And no, basically they're
Not?
not, it's not there. And in some ways that's sort of what you expect to have happen. Maybe. Yeah, but I like your analogy with the pool of water, yeah.
The video?
What's predicted that's left over after the collision?
Oh, basically, more rapidly rotating and massive neutron star. Okay, and that's sort of what it is that you see. If there were any irregularities on the surface of the neutron star, then you could also end up with gravitational waves. But got a smooth, billiard ball, or even smoother than a billiard ball.
Oh, I did.
Yes, not bad. Be careful.
Or we could just like let you walk back and get to talk. I can just speak. Okay. So moving from what's new to what's up. Brian will be giving us a rundown of what is currently in the night sky, including a conjunction happening on Sunday or Monday.
I made it up for Sunday for some reason, but we'll talk about a little bit about it. Okay, so this is what's up for November. I apologize for my lateness and a number of projects at work to finish off. Okay, so Mercury. Well, basically it's going to be a day planet. We achieved it wrong, or the greatest eastern elongation, I believe at the end of the month. Venus, again, be another day planet. I'll talk more about that later, because it's in conjunction with Jupiter. Mars, well, still a long ways off before we need to catch up with it in 2018, I believe. Jupiter, well, again, another day planet. What do I have? Yeah, close conjunction with Venus on the 13th. I'll talk more about that later. I have a little proposal to make about that. Saturn, well, it's gone. Saturn's one of my favorite planets, but we'll catch up on again next summer, I believe, August, July, somewhere around that time, and it's lined up with Mars. Okay, now this is what we're going to talk about. It should be the 13th, but I put down the 12th for some reason. I was thinking it's coming out on the 12th as opposed to the 13th. So yeah, here's a conjunction we kind of talked about earlier. Of course, we have Venus and Jupiter right about here. We have Mars, we have Mercury, and Saturn over here. So this is roughly about 12:30 in the afternoon. What I was thinking of doing on Monday, since I have Monday off, I was going to come out to Glenlee. If you want to join me, please do. I wasn't going to show up until maybe around 2 o'clock in the afternoon. And the reason being because these planets are pretty close to the Sun. And to be safe, we can be in the dome, and we can block out the Sun and only view the appropriate planets. Apparently some of these planets are visible during the day. I think some of them are going to be kind of washed out, especially Jupiter and Saturn, but we'll try it anyways. But I have seen Venus lots of times during the day, and it just basically looks like the faces of the moon. But I have set this correctly with the temperature in mind to see what's going to really look like on, well, actually on Sunday. So if you want to come out with me, I'll send an email out. When you join me, please do, but I won't be heading out closer to 2 o'clock in the afternoon. And roughly Saturn, here, roughly about 3 o'clock will be pretty high in the sky. So I'm looking forward to that. Next, okay, here's another view of the planets. Of course, Mercury would be the greatest elongation right about here at the end of the month. Of course, we have Venus. You can see how it's going to line up with Jupiter on the 13th and on the 12th too, pretty much. Mars is here. Saturn and Jupiter don't really move much. But just to give you an idea, the planets are rotating in a counterclockwise direction here. So same time, well, not same time, but around August, Mars would be here, Saturn would be here, so that'd be kind of interesting to see. Mars would be closer, I'm not too sure, is it 20 arcs roughly across? That's how big Mars is going to be, but unfortunately Mars is going to be pretty low in the atmosphere. What else? Okay, this is the events that we have coming up here for today, or for this month here. We have north and south. Well, the south was already happened. The south meteor shower was on the 5th. The north is on the 12th, which is Sunday. I don't know if I'll be heading out for that. Of course, we have the Leonid meteor shower on the 17th. I will be hosting that. I believe you did talk about it. Okay, good. Because that's perfect because it's Friday. You know, I don't have work the next day. And of course, what's even better is that we have the new moon on the 18th. So it would be great having both at the same time. So, and of course, we'll have the comfort of the warm room at Leonid. So if you want to join me, I won't be heading out there closer to 10 o'clock, roughly, about that, and I'll stay as long as I can. Of course, I talked about Saturn, and then Mercury, and of course, the moon is on the 26th. Okay, the north and south meteor shower here. Okay, just kind of give you an example. The only really good thing about this meteor shower is because the fireballs, like it's supposed to be, it's only going to, what, 5 to 7 meteor per hour. But one of the best things about it is it's like it's supposed to have the really big fireballs. That's kind of like more unique to it than any other meteor shower. Of course, the meteor shower, I'm going to talk about it. Okay, well, again, the nice thing about it is it's close to the new moon on the 18th. The comet Temple Turtle, right, was the debris left over from the comet that circled around the atmosphere, or around the solar. So I'm so busy with work today with this. I had a number of projects that I managed to get it. Okay, and of course it radiates from the constellation of Leo. And of course, again, I'll be hosting it at Leo. I'll be there around 10 o'clock. And okay, so just kind of give you an idea about it. I had this set for 2 o'clock in the morning. So there's the constellation Leo. It doesn't happen until it doesn't start to rise until 2 o'clock in the morning. So I expect it to be, it's going to really peak probably around 2 o'clock in the morning. So please, if you want to join me, that'd be great. Hopefully it'll be nice. Now, of course, another factor would be is, you know, it's going to be clear. Okay, so it's kind of rare that we actually have a new moon and it being clear. Wait, of course, is Stan here? No? Okay. Because he had some unique way of keeping yourself warm, was it? A couple years ago? Was it that battery pack thing or something? Was it?
Set himself on fire.
Yes.
Okay, that's...
Well, he denies it. He organize the event.
Unintentionally. Or intentionally, I don't know. It's Stan.
So I'm looking forward to that. So like, hopefully we're going to be out there together. So that's it. That's all I have to say.
Okay, we'll break for refreshments, and then at about 8:45, we'll come back and do RASC and Expert. Email address is correct, and you read your email. You would have seen me sending you a couple emails about this RASC and Expert idea that I came up with. Super creative and original. Panel of people talking about a thing, right? I mean, who's ever heard of that before? Yeah. Thanks, Dan. But anyway, one of the things that I do love about this club is that we have a lot of really smart people. I couldn't find any, but I got these jokes, whatever. But we do have a lot of really informed, smart people in this club. There's a lot of knowledge to go around, and I find a lot of time we don't really get a lot of opportunities to ask good questions. I also find that sometimes people are afraid to ask questions, and they may feel like it might be done. Who knows? So what I did was I sent out an email to as many people as I could to say, hey, submit your questions. They were all submitted anonymously. We got quite a few of them, especially in the past couple days. Classic. But there were a lot of really good questions. We won't get to all of them. I also took a couple of questions and maybe merged them into one, that sort of thing. So we'll try to get through as much as we can tonight, and then we'll see where it takes us. So I'd like to introduce our expert panel. You guys are sitting out of order for how I'm doing this, but that's okay. First up, we have Ian Cameron. You see him here every single month. Some interesting facts that I learned about him 5 minutes ago. He built his first telescope at the age of... I didn't learn these facts, sorry. Preteen, yeah. So, but yeah, he is. He goes by the title of retired astronomer. After that, we have Danielle Hood, who has been with us. Contributing. She's given us at least one feature presentation. She spoke at Spruce Woods for us. Her research area. So she's an instructor at the U of M in the Department of Physics and Astronomy. Her areas of research are mostly in solar wind. Stan Runge. So Stan's been my socks match? Yeah. I don't know if this is a mistake or grabbing everything. No. Stan's been a member of the club for a long time, and he has contributed significantly to it over the years. And he's also I found him to be extremely helpful and knowledgeable and willing to share his knowledge of astronomy. He also has an asteroid named after him, which I think is kind of cool. Holy cow! Yeah, that happened this summer. Pretty neat. So what happened there? And then we have Jerry.
Three cheers to Jerry.
He's just his guy, you know. That's okay. Okay, so we're going to jump into the questions. And so the way this is going to work is I'm just going to throw the questions up on screen so everyone in the room can see them. Except for you. I just realized that was a terrible idea. I can read them out, yeah. I can read them out, or I can move the laptop down there, actually. That might be easier. Yeah, we can move the tables. That's a little far. Okay. We'll be We're good. Okay, and then what's going to happen is we only have one microphone, but what will be happening is they'll just be taking questions as they come.
So, first question. Nice and basic. Why are the planets and stars round? Who would like to take this one? Who's cracking anything?
I'll start.
Okay, go for it.
Katie already said she's got this one.
I've got this one. Yeah, it's true. I went through the list and I was like, these I can handle. These are very dicey. So for stars and most things that are large and astronomical, the main force that acts on them is gravity or self-gravity. And so it's a force that's inwards and it's a force that's spherically symmetric. And by that I mean that it has, for any given distance from the center, it always points inwards and is the same anywhere for that particular distance along a sphere. And so if you have something that is massive enough, its gravity will be strong enough to pull it into a sphere. And it's because that force is the same everywhere on the surface of the sphere. Would anybody like to add anything?
With the exception.
With the
Then you do things like the planet Jupiter. Right?
Yeah, I was going to
And if it's rotating fast enough, then it's got a secondary force that actually makes it not exactly.
yeah.
I was just simply going to add another sort of prosaic thing. It's why you won't get mountains so high on different planets. So they can only grow so large before they basically smoosh under the moon. Is smoosh a good technical term?
Smush is entirely acceptable.
The idea of things being round is part of our definition of planets, too. So, why are planets round? By definition. Which gets to be a bit of an annoying thing. I've got a soapbox here, so I'm going to rant tonight. But, yeah. The IAU definition of planets, round, goes around the sun and cleared its orbit. Everybody fights the cleared its orbit thing. We've got exoplanets now, and so we're going to have a whole new set of rules written to try and accommodate those. But I think what we should worry about is just even the narrow parts of the definition of things like sphericity. How just because it's round, goes around the sun, and let's say there's nothing in its orbit, that could be just a ball of water that happens to be the right distance from the sun, and if there's nothing else there, there's nothing in its orbit, it could be very tiny, and it'll be spherical, and it'll do it under the proper conditions. Does that count as a planet? No, they won't want to call that a planet, because it'll be too small. So the best of our definitions seem to be leaving us with some problems, but I'm not going to go into it any further than that.
You got the mic.
Okay.
Next question. Yeah. Thank you. Question 2. Why do we only see one side of the moon?
It's tidally locked. Those people will give you the real fancy definition of how things get tidally locked. But what I found really interesting about this question is, how long has it been tidally locked? And it looks like from the theoretical descriptions of it all, it's been locked a long time. Matter of fact, it probably formed and was locking up at that point. It may not have had a lot of spin to it, except if it had been smacked or bashed around. But before you get to that, you have to get some of the history of the moon. And the history of our moon, by our best guesstimate, is that, okay, the very young Earth got smacked by a Mars-sized body and splooshed a bunch of stuff into space, which eventually coalesced into the moon. And then as this coalescing took place, the material got locked in. But I'll let those experts tell you more about it.
I think I forgot what I was going to say. Oh, YouTube video, Astro Girl West. Somebody you all know, okay? Jennifer has produced one which has been on there and has had an incredible number of hits for quite some time. And so I really want to see it done in excruciating detail. Yeah. The other thing is, just take a coin, try to move it around you, okay? And see what happens when you don't rotate it.
You saying the moon is flat?
I'll go there.
Jeez. Okay.
You guys got anything else?
Yes.
we had lumpy planets like we have Dome Lake Jupiter, we could easily have, you know, a couple of binary stars within RASC limits that turn into fancy lobes and things. We're okay with that too. We're saying it's going to be round if there's nothing else booting it about.
No, good, thanks. Yeah, actually, if you guys have anything from the board, just let me know, and I'll keep an eye out for hands as they go up.
We might even actively solicit.
We'll see when we get to the fun ones. Okay, is it possible for stars to have ring systems?
Yes, this is a really great question, and the answer is yes, sort of. We don't really call them ring systems, but most things start in giant cloud shape and then condense. And as they condense, they need to conserve angular momentum, so they start rotating faster, and so they'll condense into something spherical and then pancake shape. The same way that a ball of dough will flatten as you throw and spin it if you're making pizza dough. And so this is true for planet formation and for star formation. And so you'll often get protoplanetary disks, so it'll have a young star in the middle, or it'll be a disk with a bulge, and so you get a young star in the middle that has this dust disk around it. And as that evolves, eventually the star will start to fuse, and the light and the heat from that will melt away or evaporate the water and push the dust outwards. But at the same time, you end up getting formation of planets, and these will migrate. And so in the same way that there are gaps in the moons of Saturn because of its gaps in the rings of Saturn because of its moons, you'll get gaps in the disks of these star formation disks because of the planets. And so it's the same physical phenomenon but on a different scale.
If you want an example of that, the star Fomalhaut is got a disk around it. Go online, take a look at the pictures that have been obtained by the Atacama Large Millimeter Array. ALMA. Anyways, you'll see beautiful pictures of a lovely disk around that star. And it's easy to see in the sky at this time of year, so you can look at it yourself. You may not see the rings of it.
Any questions? Move on to the next one. Question 4. What is the cause of fast radio bursts? How do they differ from gamma ray bursts other than the obvious energy differences between gamma ray bursts and fast radio bursts?
If I could answer that, I think they'd give me a Nobel Prize.
So do you want to talk maybe a little bit about what fast radio bursts are?
Sure. They're, if you like, unresolved point sources. You can find them all over the sky. They're fast, milliseconds duration. Let's see. Broadband, many frequencies. Basically, you can get a little bit of a handle on them because there's a frequency delay associated with the signals. Long frequencies are delayed with respect to the shorter ones. Let's see what else.
Probably
Yeah.
intergalactic.
Yeah, beyond the Milky Way. And I think because we're now being able to do all sky surveys in fairly short periods of time, there are more detections. So there are lots of them. And I've forgotten what the most recent sort of estimate is. Lots.
We don't know what the source is.
That was going to be your question.
I told you if I could answer that.
Yeah. Just to clarify.
The collision of neutron stars. No, a little bit different.
Can you guys hear us if we're not passing the mic around appropriately? Yeah.
Not really.
Okay. Moving on. This one's a little bit of a long one. I know, this is the Aurora question. So, it reads, I've read a number of times that Aurora is seasonal. Some comments have said winter is best. Some have said spring/fall. I always thought maybe winter was because that was merely a recognition of the greater number of dark hours during winter and the greater opportunity to see aurora. Simply, are there aurora seasons? And if so, why? This is like telegraph to you, by the way.
All right, so thank you for this question. I did not.
This is
stop.
not a plan.
No, that would have been good though. Please tell me about the sun. So yes, there are aurora seasons, and there are 3 main factors. So the first one is the length of night, so it does need to be dark to see the aurora. And so summer, especially in the northern hemisphere, or at high latitudes in northern summer, you're not going to see aurora just because it's light out. The second is that it has to do with the interaction of the Z component of the magnetic field in the solar wind, and so that fluctuates very rapidly from north to south and up to down. And that will interact with the Earth's magnetic field, which points northward on the day side, so the side that faces the sun. And so you need them to be oppositely aligned to trigger the process that will generate the aurora. And so during the solstices, the Earth's magnetic axis is either tilted away or towards the sun. And so that will change the relative inclination of the Earth's magnetic field to the solar wind's fluctuating magnetic field. And so that opposition during the equinox in both the fall and the spring is more favorable to trigger aurora. And so observationally, we see that there's about twice so on average, there's aurora about 30 times a month. And then in the fall, you get about twice that. And then in the spring, it's about 1.5 times so there's kind of this double peak in frequency. And the 2 factors that I just explained account for about 1/3 of the variability, and the other 2/3 are still fields of active research. Yeah. So we don't really know.
Cool. That's exactly what I was going to say. I was going to just ask somebody who does a lot of aurora imaging. Do you notice the difference?
In the fall, yeah, right now. Aurora season right now.
Any follow-up questions?
And it doesn't have to do with how dark it is, because you're out all times of the year as soon as it's dark, so you see all times of the year. So.
That's good. Anything else?
For people like Kevin doesn't like auroras. Because imaging, so it's basically noise. And there's been times that we've had Spruce Woods where everybody's got all their equipment ready to take all these dark sky images, and here comes the aurora, and it's so bright, and everybody's oohing and eyeing, and all the imagers are going, damn it.
Cool. Okay, next question. Help me to understand infinity, especially in relation to the size of the universe.
Philosophical question. Thank you.
Think of when you first realized it could be infinite. You probably had this as a child. If you still haven't had it yet, come talk to me later. Everybody gets this idea, well, how big is the universe? And you just get this idea, well, you can keep traveling and traveling and traveling as far as you want, as long as you want. And if you stop, you can still stick your hand out, okay? You can always, in some ways, have it go further. The idea of it having a limit is philosophically distasteful because of the idea of it having a boundary to which suggests another side, which is what? Not part of our universe? So by the definitions we're using here so far, we have a problem of talking about our universe as not being infinite. But then there's a clever way in which mathematicians, cosmologists can talk about a finite universe which is unbounded. But I'll leave that to those experts.
last point. But I think that infinity, while kind of mind-boggling, is something that numerically is not unreasonable, right? If you were to say, okay, I'm going to count in integers, you could count forever, right? There are an infinite amount of numbers. And so if I were to throw out something that had 75 digits, that's still something that's finite. Nobody says, well, there has to be an edge to integers. You can always add one. You can always add one. Right? And so n plus 1. And so you would be counting forever, but nobody's like, oh, well, there has to be a last number. That isn't a concept that we tend to struggle with. And likewise, there's an infinite number of numbers between 0 and 1, right? If I can divide 0 and 1 into 10, so 0.1, 0.2, and I can divide that into 10 again, and I can divide each of those intervals down into 10 again and again and again, an infinite number of times. And so there's an infinite number of rational numbers between 0 and 1. And so we often come across infinities in our normal number systems, if we really think about it. And so, and those don't seem quite so boggling as a physical space that has no edge. But I don't know if that answers the question. Musings.
Now, we won't even talk about different cardinalities.
Yeah, I was going to say, we'll talk about different infinities.
Because the question specifically asks about it in relation to the size of the universe. And when we get to the rant section, which is coming up, I'll have more to say then.
Go ahead.
I thought Einstein said if you do the straight line, it comes back and hits you in the back. The universe is
Romanian geometry and the whole closed space. Yeah, I mean, the physicists and the cosmologists and the mathematicians can get clever with the geometry at that point, but that's only one interpretation that might work. That's not quite the infinity that we're talking about here, because we don't know if that one really is going to be the one we're left with. So far, the universe is looking fairly flat. So.
Moving on. Question 7. Is it still believed that the universe is expanding at close to the speed of light?
The question needs to be defined more.
You sprung that one on us, right? Where's Adam? Care to comment? No.
There are parts of the universe that are moving away from each other at greater than the speed of light due to the expansion. We've got no problems with that. That's not the violation of, Einstein's speed limit, because what's happening is if you've got enough space between objects and there's any incremental expansion, there will be 2 points substantially far enough apart where to add expansion in between them will allow the relative distances between those 2 objects to be going away from each other at greater than the speed of light. We're measuring these things all the time. So, is it still believed that the universe is expanding at close to the speed of light? Not the expansion of what? The edge of the visible universe? That's not what I was just talking about. That would have to do with all kinds of expansionary factors and the Hubble constant and the rest of that. And again, I would say no, not even close. But we've got a way in which parts of the universe are going away from each other at greater than the speed of light. Which means, go look at all your objects now, because some of them are going to be disappearing in the future. We'll get at that later, too.
Yeah, I don't know if this adds anything, but essentially we measure the expansion of the universe by looking at how fast galaxies are moving, or distant galaxies are moving away from ours. But that's really just measuring, it's not that these galaxies are moving, it's that the space is expanding. And so it's fine to have geometric points moving faster than the speed of light. That doesn't violate anything. You can't have something massive moving through space faster than the speed of light. And so it's possible, the further apart the two galaxies that you're looking at are, the faster they seem to be, or they are moving apart from each other. But that's a little bit separate or nuanced than the expansion of the universe by itself.
How do we do that? How do we measure that?
We measure it via redshift. So we look at the light coming at us, and it is stretched out more red than it ought to be.
Does there not be a limit on that?
Is there a limit to redshift?
In the visible universe? Yeah.
Well, we haven't kept going in terms of the redshift.
We've got a redshift on the cosmic background microwave radiations. That's a limit.
Which I also think is kind of interesting, because at some point in the distant future, there will be civilizations who won't get to see the scenery. Which opens up some interesting thoughts about what they might go through.
It gets complicated.
So everybody understands redshift, right? Yes.
Yeah, that's a good explain actually.
The whole concept.
Stan, what is redshift?
Well, we expect to see certain things at a certain particular frequency, certain band of light. When things are moving away from us, it's like the Doppler effect. You hear the change of sounds of a train as it's coming to you and going away. It's the same thing as something that's going away from you. The sound changes. Well, we see that change similarly in light, in the spectra of light. So things that you expect to see here, you see way over here. And then from that, you can determine that that's moving away from us. And redshift is the whole deal of shift is a great thing, because we use that a lot. I mean, we look at galaxies, distant galaxies, and we see them rotating. And we're using this to see that one side of the galaxy is coming this way, the other side's going that way. And it's when they really started to do that, they started to determine, hey, wait a minute, that galaxy is not turning at the rate that we expected based upon the models that we had. And that was the big shift that happened in the past century, that all of a sudden determined there's got to be more than just the material that we see that's going to cause that. So redshift has really been a really key thing for us to learn a lot about our universe and learn a lot about matter, and in fact, help to introduce the fact that there's got to be some dark matter or something else out there to change things. Good? No, that's good.
Yeah.
Dumb question coming up.
Yeah.
In your definition here, you seem to indicate that there is the outer edge that you see in the universe. Isn't that by the same definition saying it's finite?
No. and the longer answer is that...
We're going to need more beer.
That's the longer answer.
And so the longer answer is that we can only see as far back as time, we can only see as far back as photons have been able to freely travel towards us. And so there's the time of, I think, last ionization. My cosmology is rusty. But yeah, so when the universe was first born, it was essentially a hot, opaque soup of protons and electrons, and the electrons would interact with the photons in such a way that they couldn't go anywhere very fast. And so the universe needed to be cold enough for the hydrogen essentially to be neutral, and then the photons could travel freely. And so since that time, there has been 13 billion years. And light can only travel so far in that time. But that doesn't mean that we're seeing the edge of space. It means that we're seeing whatever is within that travel distance. So there could still be stuff.
We're seeing through the fog.
Yeah.
Good question.
That's why the term visible universe is always being used in a lot of these conversations. It has other meanings that physicists like to throw on top of that stuff, because you can start talking about the Hubble sphere as well, which has to do with how much of the visible universe is still something we can interact with because of the limitations of the speed of light, blah, blah, blah. Lots of complicated definitions here. As an example, you might think we can give you good, straight, solid answers for all these questions, but all of you have a fairly good command of the English language, and yet a lot of you would probably have trouble reproducing Gödel's incompleteness proof for why the English language can't say all the truths there is. So we're facing the same kind of problem here in arm-waving about some of this astronomy stuff. But,
there is an apparent horizon around everything. Any observer has an apparent horizon around it. And that if two galaxies were to go separate from one another faster than the speed of light, the light from that galaxy would never reach you. And so it would slide over your horizon, and you'd never know that it was there.
Their two visible universes would be not entirely overlapping then.
Yeah, I mean, depending on who's observing, right? I mean, everybody's got this horizon around them. Every observer has a horizon. So
I feel so special.
Like the question that was brought up too, like visible universe does not mean the entire thing, right? Because you can only see back so far.
And especially if you combine that with the idea of the universe really being infinite. And hopefully we'll get to talk about that a bit more if that other question comes up.
It will.
And the other complicating factor is that you have to consider where the galaxy or light source was when the light left and not where it currently is now. So if you have a galaxy that it was very close, well not very close, but was closer at one point so that light could reach to us, but the universe is expanding at such a rate that light that's leaving from it now will never get to us. As Jerry has alluded to, there will come a point where there are things that we won't be able to see anymore.
Moderator? Yes?
I think the person that asked this question, he's wondering if from a fixed point, is the universe still expanding at the same rate it was before? My understanding is it's expanding faster. And I think that's the question he's wondering. He didn't say that, but I just wondered if it's still. He's asking if it's expanding at a steady rate, and I believe it's expanding at a faster rate.
So the question is, sorry, so just to be clear, so you're asking what is the expansion rate of the universe?
Has it changed?
Yeah, the rate of expansion has changed over the lifetime of the universe quite drastically. There was a period very, very early in the universe, in 10 to the minus 29th or something like that, when the inflationary period started, which all of a sudden went from something tiny to boom in almost no time. And so that rate of expansion was many times the speed of light. And then supposedly it's slowing down up to a point, and now it's accelerating upwards. The expansion rate has never really been, I don't think, ever considered to be a constant rate. It's been, over our lifetime, we could sit there and dial up a Hubble constant like we're starting to do, but I don't think that's all that significant.
So, Carl? Cool. All right, moving on. We'll eventually get. We will eventually get out of the cosmology, I promise. Yeah, right. We're kind of trapped in here. So this actually ties in a lot with what was being asked. So we are able to see galaxies that are almost 13 billion light years away, ones created shortly after the Big Bang. Since we all started at the same place after the Big Bang, what have the photons we see from the distant galaxies been doing for the last 13 billion years?
Traveling at a constant speed towards us.
That's what I was in transit, but Jerry's got a much more interesting take on it.
So they've been dancing, wearing silly hats.
Yeah, and you indicated something in your earlier response that relates to all of this stuff. It's like, you've got to know where these things were when they emitted those photons. Now, I I had a piece of paper with me with a bunch of numbers written on it, and I've lost the damn thing. So here's what's going to happen. I'm going to tell you what I remember, but you don't hold me to these numbers. But there are some rough guesstimates. And cosmologists are really annoying. They will all tell you things like, here is the redshift of an object that we've determined to be, 13 billion light years away, which is now at 46 billion light years away in cosmological now time. In other words, when it emitted the light, it took 13 billion years to get to you. And now that object is 46 billion light years away from you, but they don't tell you where it was when it emitted that photon. You have to do something called the Friedman-Lemaitre Walker matrix calculation to figure out, it's the actual stuff of general relativity that Einstein laid out. You have to do this calculation to figure out where stuff was. So that's why I had a piece of paper that I've lost. Anyways, we talked about the photons finally being free. They've got a number for that. At 380,000 years. I mean, that's a pretty exact number by astronomical terms. The photons were free to travel. They couldn't go very far because everything was still a soupy mess, but that's when they decoupled and were able to at least be possible to be out there. Not long afterwards, you've got the ionization era where you've got what we see as the cosmic background radiation, the Wilkinson anisotropy probe that gave us the lovely pictures you've seen of all the little evenness of the background radiation, was apparently now at the furthest reach of the universe that we can observe. And so they're saying, yep, that's now at 46 billion light years away. Where was it when it emitted those photons? And so you can do this Friedman-Lemaitre, no. You can do this calculation. And it turns out that when you do the math on this, that background radiation was emitted a mere 42 million light years away. That makes for a pretty cramped universe at that point. And they've done, it's so hard for these cosmologists to give you the early numbers on this stuff. And here's one of my rants that I'll get out now, but the whole deal is, this is 13 billion years in traveling to you. It started out only, 42 million light years away, and it's now at 46 billion light years away. What I want to know is, these numbers we use when we convert the redshift numbers into distances, the way Hubble wants us to do here, it works okay for the shorter distances, but it gets really screwed up when you try to do these far away things. One other calculation I found that I just remembered the numbers for, something that is just 13 billion light years in travel time, it was emitted when it was 3.4 billion light years away from us, and it's now something like 29, 30 billion light years away from us. And it gets to the point where, what was that first number they first gave us? Well, what good is that number? The 13 billion number. It's like, we say, well, its travel time is 13 billion years, so it's 13 billion light years away. Well, no, it wasn't. I mean, it was actually a lot closer to us because of that Friedman-Lemaitre, that whole thing. So we're always we're doing bad science sometimes here when we take things that are really an age determination. That photon was traveling for 13 billion years, but that wasn't to say that it was 13 billion light years away when it emitted the photon. And this was just one of my rants about the way in which this gets really complicated, and sometimes the numbers and things that were given just don't make a lot of useful sense to us.
The drink, Jerry.
Yeah.
I kind of wonder if that's somewhat conflated with just the way that I think in astronomy we're constantly reminding people of what the speed of light is and how far a light year is and that sort of thing. And I think it enters into this kind of common theme that okay, this is how that must work, right? And then because that has been drilled in so much that to have any other considerations for it seems wrong and weird. And that might be where the source of this question comes from.
Well, I'm bothered by it in one sense because one of the things we love to do is say, when you take a look at the redshift of, say, the Andromeda Galaxy, or we can actually measure its distance with much more reliable methods. We've got a situation where it's 2.5 million light years away, and we can tell the audience the light that left that galaxy, has been traveling all that time, and that's its distance away from us. Of course, like with Andromeda is not the best example because we've got other ways of measuring to Andromeda. But to the further objects and to things like quasars, we're always talking about them being very distant objects, and we will convert the travel time for the photons to us into a distance. And without doing the Friedman, Lemaitre, blah, 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 so four names in their conversion, this metric conversion, you really shouldn't be saying that about where these things emitted their photons, where they were when they emitted the light. Because things are always moving. Like, are you following what I'm trying to get at there? Everybody's...
Can you start over again, Jerry?
Let me start at the beginning.
Does a photon of light travel forever if it doesn't hit a body or anything else? Does it just keep going? Or does it stop?
Does a photon travel forever if we don't stop?
What's the half-life of a photon?
Oh, it apparently does have a half-life, but it's a very long one. But the thing is, it might get Hubble redshifted beyond its usefulness as even being considered a photon, I'd imagine.
Like when I see that light, does it stop? Like does that photon stop?
Yes, you've destroyed that photon.
Way to go, Sheila.
It entered your retina and died.
That was a nice photon we had once.
It's your camera.
It's instantaneous.
So it thinks that I haven't gone anywhere, and it's smacked right into
Sheila's
camera. That's the marvel, right? Traveling at the speed of light, all the things that are different. I had a conversation with somebody just the other day about that. To that photon, it hasn't then gone anywhere. It hasn't been around for long. Could have been going for 46 billion years.
No.
Anything else? Cool. Okay. That was almost. All right. Moving on. So now we're drifting out of the cosmological questions. And this is a good one. I got asked, I've actually been asked this several times, but I don't think I have a very good answer. Well, I don't know, I have an answer, but what is the best telescope for beginner and why?
Who asked the question?
You can't, you've got to write it on this.
And that's how I'm going to start it. Specifically.
That's a good way.
Okay, there's a bunch of people here, and you all got your first car. Who bought a real small car for economical? Who bought a truck as their first vehicle? Why isn't one of them better than the other? And that's sort of where, when people ask me about what's the best telescope, it's basically, what do you need it for? When a person's going to go out and buy a telescope, they truly should be thinking along the lines of what would I like to do? And that's a hard thing when you just get into the hobby. Because Jerry and I know the solution to that. You don't just buy one. Buy like 15, 16, and then you've got all you need. So truly, it depends a lot upon the person, where you are. If you're young, you may be wanting something, because you're going to be doing pictures for a long time, so you may be wanting to get something that comes with a nice equatorial mount that tracks. Or maybe you enjoy the ability to go and see things that are really faint. So you realize, well, if I buy a smaller refractor, I'm not going to be able to do that as well. I really would like to get something that's a big light bucket. So now you want to get something that's bigger. But if you're older, and there's a few people with gray hair out there, as I can see, you start thinking, well, this is a pretty hard telescope to haul around. So if you're in your 60s and you're looking for your first telescope, you're not looking for something that's 100 pounds of weight. So it's really a question that's more tailored to the individual. So here's what I've come up with for a lot of people. That probably, depending upon whether you want to do astrophotography or not, and it also depends upon your budget. If you've got the budget that Jerry and I have, well, you're going to get something, the best cost, whatever. If you've got the money of Jay Anderson, well, then you get a Takahashi, right? We get the Tasco, you get the Takahashi. And then, yes.
My banker wants to talk to you.
The best telescope for a beginner is borrowed, so you can figure out if you like it.
And that truly is the reason why we developed that program. We've got now we have a solar scope to go with it, so people can decide whether it's fun to do solar work. And I'll tell you, it is kind of cool when you see these prominences. Hey,
I'm not saying.
So that's another of it. That's just another telescope. So if you're going to be using a telescope, at night, where are you using it? Are you using it from the city? Are you using it from there's so many questions. So we have a couple of scopes that we have the people get to come and use it, and that's a good starting point. So you take out a loaner scope, you use it for a month, and you say, okay, this is pretty good. And then you start talking to some people, and you say, hey, Kevin's got a picture in the latest calendar.
We weren't supposed to say that.
He's Mr. March.
It's not that kind of calendar.
So then all of a sudden you decide, well, I wish I'd got a scope that's got an equatorial mount on it. So we'll put on the path of a few first scopes. The first big scope that I got of any happened to be one I built myself by buying a mirror and buying a tube and buying a focuser and buying something to hold all as well. So we were part of the APM days where you get the biggest mirror that you can afford and you put it together. Mine was a 6-inch f5 telescope. And then I eventually had this plywood, pieces of plywood and pipe that made the equivalent of an equatorial mount. It was only good for one latitude, 50 degrees, but so that when I'm looking at things, I could actually track the stars by only following in one direction. You made it smoother in one way, so once you found the object, you only had to pull it along one way. So that's what I did, and that was a mainstay for a lot of the stuff I did. Now, Bill's out there. Bill had more money than I had. You got yourself a C8, right? That's a Schmidt-Cassegrain. Why? Because in those days, compact portable, equatorial mount, had large light bucket capabilities, and it was a good best of scope for a lot of reasons. But some people find now lifting an 8-inch or 11-inch Schmidt-Cassegrain onto a mount is kind of overwhelming and hard and heavy in the mount.
Or just the mount itself.
Yeah, now you want to get a lighter mount. So truly, it's a question that says, you got to decide what you want to do with it, and then and such.
And where you're going to use it. For instance, a lot of people would suggest that, probably the most versatile jack-of-all-trades telescope is something like a Celestron C8. If you're going to use a C8 in Winnipeg for half a year, you're going to be in for a lot of frustration because that telescope is a bit fussy when it comes to the weather. It has a corrector plate up front, which is a dew magnet, or in this case, a frost magnet. and it's going to be a telescope that, so you should not only ask yourself, well, is this the telescope that's going to work for me? Is it going to work for me in winter in Winnipeg? So you've got a lot of factors besides who you are and what you want to look at. You want to consider where you're going to use it too.
Now Mike is here, and he's going to tell you probably the best, right? Probably the best scope is to get a refractor, right?
Well, for different reasons, yeah, it is. I mean, but it all depends on what your goals are.
Mike likes planets, right? Admit it, Mike. So he's one who's, so, you know, if you're in the city and you don't get out a lot, and you're not going to be doing a lot of stuff where you're going to get underneath the dark sky, well, looking at the sun, the moon, and the planets is one of the easiest things to do. It's the brightest and the best objects. So he's got a refractor, which you spend 10 times more than you do for a reflector, but you get quality imaging coming out of most of them, right? His is an apple, you know, so apochromatic. So his doesn't have that, you know, blue on one side and yellow on the other side of the image. You don't have those different colors and these brilliant colors. So in his case, if you're looking for planetary, you should probably get yourself a refractor. If you're older and you don't want to be carrying big scopes, they're probably good scopes to get, because guess what? You buy the smaller scope and you get a smaller mount to go with it. So it's handy for that. It's the devil is when you want to get into photography. then you put a big scope on it, and now you need something that's got to be precise, and now you're talking weight. So,
Okay, moving on.
There's actually a lot of expertise in the club. Ask around.
Yeah, definitely.
This is talk to people. Okay, find out what they're doing and what equipment they're using, and you'll find out how much money you want to spend.
also lower scope program. Yeah.
Sure.
Yeah.
And go to. You get back into the whole world of go to. For some people, they want a scope that's easy to use. One of the funniest things that we run into, we're down in Arizona, and we're up in a real dark site, 6,600 feet, the Chiricahuas, and you know, and the guy shows up and he's got his go-to scope, and he's all excited, and he's in deep skies and all this, and he pulls out his scopes and he sets it up, and he comes over and says, "Any of you guys know how to use this?" Literally, he didn't even take the time to understand how to even get his scope started up. And you know, it's like phone. I don't know how you know, what buttons to press on your phone to make it do certain things. You've got different operating systems for different scopes. Mounts have different operating systems. So yeah, you know, there's another realm. So do you want something that's just going to show you stuff? Well, then maybe go to. Or you're an adventurer and you want to find it yourself. Both have advantages. Somebody who has a go-to scope gets to see more objects in a shorter period of time. But then there's something about finding something, the hunt for something. If you want to go searching for comets, or you want to see things that are moving quickly, then you know, then you've got to learn how to find things and go search for things. Or if your battery dies, then your go-to is now one scope that you have to figure out how to go find things on your own.
Okay. Thanks, Dan.
Question.
Yeah.
Just for as far as actually looking at, so we're looking through other people's scopes, member events like the Star Party or observing nights. It's a really great opportunity. When I was at the Star Party, like I don't have my own scope, and everyone here is really excited to let you look through their fancy scope, and you can kind of get a feel for what you like, what you don't like, if you don't have one.
One of the things we do at Spruce Woods is during the daytime, we have a session where people show their scopes or show the equipment that they're using. And that's a wonderful session, because that's when you really get down to deep, down and dirty. And then that's when you hear the dirt on it, that's when you hear the praise about this. This is really good, or this is really bad. And like, you know, like Jerry was saying, on nights that, where it's going to be frosty, well, you know, having a Dobsonian telescope is great, because you know, it's down this tube and that near, won't get dew on it for a long time. You'll be able to use that scope for quite a while that evening. Other scopes have got to have a heater going, and battery pack, and all that stuff. John, what was your first scope?
Mine?
Yeah.
It was
Sears 60 millimeter Acrobat, 900 millimeter focal length. It was a beautiful little telescope for what it was.
On an equatorial mount.
On an equatorial mount.
Yeah, and that's from the days of old where the actual store-bought telescopes are actually...
Well, you could actually still get a reasonably decent telescope from a store. You can't do that anymore. You've got to pretty much go to a specialty store and get telescopes.
So you heard somebody who got a C8, somebody who got a was it 60?
It was a 60 millimeter.
60 millimeter, and I got a 6-inch scope. So, and we're all about the same age at the time, so it was kind of what we did. Bill still uses his C8. In fact, he just got a new mount. Do you use yours?
Mine is a C8 now.
Yeah, see, he's changed, and I've gone to bigger scopes as well. So.
I still use my 6-inch. 6-inch Newton.
Yeah.
One of the best scopes I ever had.
Okay, just keep rolling along. Just gotta get it. Because the next one might go on a little bit too. How about you ask for photography from within the city?
Well, you can.
Well, maybe this will be short.
You can. In fact, yeah, right? The day of digital cameras is the thing that has really changed things. When you take a digital image, you can later on go back and process it. And processing is basically taking information, which is a count of light, of number of photons trapped, destroyed in one pixel, in one slot, right? And then you have a program that looks at all these different pixels, all these millions of pixels that you have, looks at each individual thing, and you can say, well, do something to it. Subtract 100 photons, or a level of 100 count from each one, or decrease it by 100 count, or do this and that. So with processing, you can start to do certain things now and such. There's a thing called a histograph. When you take an image with a digital camera, you can have the camera show you a little graph that shows you where the light has been captured and different levels of light and how many spots it has in these different locations, different levels of light. And you can take that and you can stretch out with computer processing. You can stretch out and you can actually pull detail out in photographs. So in the city, there's a couple of things that you need to do. You need to, one, make sure that you take an exposure that's short enough that it's not overwhelmed by pollution. The second thing is that you, in order to take a proper exposure, you will take many, many frames. Like you'll set your camera and say, okay, take this 30-second exposure and take 20 of them, or 40 of them, or 60 of them. And then ultimately you'll have a computer program that'll take all that data, combine it together, and what happens when you combine it is you reduce the signal-to-noise ratio and you start to get more detail out of it. There are certain filters that you can use. And the filters are, they're called LPS filters, light pollution filters. They were really good because they could really do an excellent job on killing the sodium lights.
Yeah, not so much the LEDs.
So that is the issue of today. The one benefit is that the LEDs are throwing out less light out all over the place, less light up into the air to reflect off the dust particles, but they're really bright in the wintertime when there's snow. You can't. So one person who's been doing a lot of this is Mark. I'll put your hand up so everybody can. So what do you find helps you with the most success?
Pardon me, what was the...
The most success for getting imaging from the city, because you shoot from the south part of the city.
I do mostly urban astronomy and urban astrophotography, and it's basically using a CCD camera. I started out with a DSLR and removed the IR filter, ultraviolet filter in the camera, and that helped a little bit, and tried with filters, but found the CCD camera the most effective because of the variety of filters you can use with the camera, and then and that's been my the area that has the most success with is really hydrogen alpha, sulfur and oxygen filters. Like narrowband filters that really eliminate all of the stray city light. And then it's a matter of combining those images together and building false color images, the Hubble palette, basically. So, and that's kind of the most effective approach to urban astronomy I found anyway.
Thank you.
But it's not cheap. So that's the dilemma you face.
Focus on the planets.
Yeah, that's a the sun and the moon. The moon and the sun. Definitely do those. Okay, that was good. I think this. Okay, we'll try to get through the last couple. These will be I don't know, maybe lightning roundish. I need a new autoguider. Stan, what do you recommend?
Well, somebody's asking for an autoguider that does not require a computer to use. And I know at Sidelines, I'm trying to think of the model name of that one. Remember that autoguider that you could have that you could plug in and go to school?
I remember.
Do you know what it is?
I can't remember. I lent it to you.
Well, I tried it and I didn't like it. Johnny has it. But are there any more that are on the market right now?
Yeah, because I think it would be worthwhile, especially if you have a laptop in the field, because you need to see what's happening to your image. If the telescope's bouncing around, the star's bouncing around, you're not going to get a half-decent image of it. So it's going to have a visual.
Yes, you need the laptop.
You need a visual confirmation. SBIG makes one, it's the STI, and you shoot it once or twice, and it kind of pre-programs itself, and you bring it out into other environments, but it doesn't always have the same.
Yeah, we haven't looked at autoguider. We have it so it's on a chart, and the chart will show you how well the imaging was going. And the bottom line is, if you're looking at that, you're seeing that the camera, or that the guiding system is having a problem trying to keep that star in the center, and therefore correcting your scope to make sure that the star is the center. If the sky isn't giving you the imaging, you're not going to get good images.
Especially if it's turbulent out there, and the guy will follow the star that's bouncing like a ping pong ball. So you get your image, guess what? It's crap. It's too soft to use.
Right. Okay. Let's see what we got left.
I'd like to go back to that question. So maybe a corollary to that last question is it worthwhile to look at something like an autoguider that doesn't require a laptop, or is just basically what's in the marketplace is not worth the effort, and if you're going to go into guiding, auto guiding, you might as well commit yourself to using a laptop?
Well, that's been my experience. That's just, my experience. So it's limited. I tried this one, and I was not pleased with it. And I used the star guider that you get from Orion. It's about a $350 little unit. It plugs in. I have it plugged into the back of an old 8x50 finder scope. So remove the lens off the back and put this on. And it'll guide for scope of about 1,000 millimeters of scope, and it works well. So that's what I've been doing, and yeah, it does. When you get into astrophotography, there's a few things that you can find out. It takes a lot of money, it takes a lot of power, and probably a lot of the stuff that you do is associated with using a laptop, because you always want to be monitoring it. You want to be looking at the images that you get to see if there's a problem. If you use your camera sometimes, take a whole bunch of pictures of it. I've done this. Shot a whole meteor shower and thought, geez, I can't even see one. And then I went and looked at images, and I had donuts. And everybody, they're tiny donuts. Really small donuts. Anybody who understands that means that it wasn't absolutely in focus. And if it's not in focus when you meteorites, when you need focus, and then you get nothing. So having a scope, having something to look at it.
No, just saying some CCDs have the ability to have a track and accumulate. So it'll take a picture, it'll guide it, it'll go back and take a picture. It takes twice as long, but it does simplify it.
Okay, makes sense. All good? Cool. Somebody decided to send us an essay in the form of I think it's almost like one of you referred to as like an exam question. I think the answer to this was yes. Last question. What commonly held astronomy myths do you wish would stop being promoted? This will be our last question of the evening, just because we're running through time a lot.
That Mars isn't going to be as big as the moon. Somebody put something out. They dropped the part that said it at 100 power, and that was only for the 1 year when Mars was 25 arc seconds. And every now and then, years come by, and all of a sudden this gets republished in August of the following year. And Mars is this one starts.
From an educator standpoint, that astronomy is hard. I get that a lot. Oh, what do you do? Oh, I have a degree in astrophysics. What? I've had people just like stop talking and turn around and walk away.
I used to hang out. When I went to the University of Toronto. I used to hang out at the Fine Arts College, and you gotta talk to girls and stuff like that, right? And one of the first questions would be, "What's your major?" Right? It's like, oh, it's like like dance and music and stuff, right? It's like, how about you? Computer science. Oh, that must be hard. Yeah, and just the complete like.
Yeah, there are often two responses. That one, we're like, that's super cool, and then a barrage of questions. Yeah. And I much prefer the second one.
So the only argument I have to the point of view is that the mathematics. If people aren't mathematically astute, then it's very challenging to know about math.
Yeah, I agree. But I have the advantage of having a math teacher as a mom. But
I kind of feel like
I think math is another one of those things where this comes from a very biased perspective, but it's systematic, and I understand that it can be very confusing if it's not taught properly. But I do think that it's within people's reach to learn.
No, I would very much agree. I really think that math is not as hard as we teach it. I think that we teach math in ways that make it not enjoyable, and that leads to it being difficult.
This is the astronomy club, not the dance club.
Yeah.
When I was employed, there were a lot of bizarre things that came via the phone, and I was Danielle's nodding, yes. All sorts of things, and some things I just didn't have a clue about. Is I guess what I appreciate is somebody who comes to me with a thoughtful question. In other words, they've thought about it for a little while, rather than the latest jazzy, as Stan suggested, supermoon! Or there were some other colored kinds of moons other than the blue moon, I think, that also terminology and those kinds of things. But fortunately, I don't have to field those questions anymore.
We're still around.
The Big Bang.
Yes.
It's not so much a myth, it's a problem with just a really, really bad name. And it conjures up all the images you see on TV. They love to show you explosions, and even on shows where you've got respectable people like Brian Cox. Is he still respectable? Anyway, you've got all these wonderful shows showing the Big Bang, and even though they caution you about things, one of the things they do tell you about is that it's not this explosion that they show you anyways. And that seems to be such an annoying, it's not so much a myth as it is just a misrepresentation of what the origin of the universe is. So many of the questions we had tonight, talking about infinite universe and such. So you don't get this point exploding out and giving you the whole universe. There could be an infinity that started expanding. So just wrap your heads around that. No point, nothing flying out from this, something that's infinite. And not just linearly infinite like we were talking, but all around. And the one that's most disconcerting to me is below you. An infinity in that direction, which can sometimes get even more unnerving for us. An infinity that could come into existence and expand at the rates at which we start describing. And then we reduce it down to this cutesy term, Big Bang, and talk about things being at certain points all along, when in fact the whole thing might be a horrible misrepresentation of the ultimate nature of our reality.
Very well
So thanks everyone. Thank you so much for submitting all the questions. I'm sorry that there were several that we weren't able to get to. Another round of applause for the experts. That was thank you to everyone else in the audience who contributed and gave some answers, some other pieces of feedback. We will now be heading to Boston Pizza to carry on these fun conversations. So if you'd like to join us, feel free. Good night.